Dear students, mm, welcome to the chapter Chemical Bonding and Molecular Structure. This is chapter 4 of your class 11 science chemistry syllabus. Now, I would like to revise again quickly whatever has been done in my previous video in this chapter. Now, before going into depth on this chapter, there are a few important things we need to understand and remember. What is Octet Rule? First, what is Octet Rule? The Octet Rule dictates that atoms are most stable when their valence shells are filled with 8 electrons. Now, it is based on the observation that the atoms of the main group elements, that means main group elements are what? 1, 2, 13, 14, 15, 16, 17, 18. They have a tendency to participate in chemical bonding in such a way that each atom of the resulting molecule has 8 electrons in the valence shell. So, the octet rule is only applicable to the main group elements. Keep in mind, this is one important point to remember. The molecules of the halogens, oxygen, nitrogen and carbon are known to obey the octet rule. In general, the elements that obey this rule include the S block and the P block elements except hydrogen, helium and lithium. Now, my dear students, the octet rule can be observed in the bonding between the carbon and oxygen atom in carbon dioxide molecule, which has been explained over here. 1, 2, 3, 4, 5, 6, 7, 8 electrons. Carbon is octet satisfied. At the same time, the two oxygen on the side, on either side of the central carbon atom, they are also, obeying the octet rule. These shared electrons fulfill the valency requirements of both the bonded atom. Thus, it can be noted that both the oxygen atoms and the carbon atom have an octet configuration in the carbon dioxide molecule. Okay. Now here, oxygen has 6 electrons in its valence shell. Carbon has 4 electrons in its valence shell. Oxygen has again another 6 electrons in its valence shell. So if we add this electron, 6 plus 4 plus 6, it comes to 16 electrons. Now these 16 electrons you must arrange in such a way that the octet of all these 3 elements is satisfied. That is why we have like this. Okay, so this is a Lewis structure representation. Okay. Now, next, there are some exceptions to the octet rule. Okay. Now, my dear students, not all elements and compounds follow the octet rule. Now, some of the exceptions to this rule are listed below. An ion, atom or a molecule containing an unpaired valence electron is called the free radical. These species disobey the octet rule. However, they are very unstable and tend to spontaneously dimerize, means form a dimer. Dimerization means, suppose you must have learned in your lower classes, aluminum chloride, it dimerizes to become AlCl3 twice. Okay, that is called dimerization. Since the first shell can only accommodate 2 electrons, elements such as lithium, helium and hydrogen obey the duplet rule instead of the octet rule. For example, lithium can lose an electron to have the stable configuration in which the valence shell holds 2 electrons only. Now, in the case of these elements, hydrogen, maybe helium or lithium, due to the presence of d orbital, the transition elements do not obey the octet rule. The valence shell of these atoms can hold 18 electrons. So, at the same time, remember the d orbital elements, they will not obey the octet rule. Only the S block element, P block element will obey the octet rule, with exceptions like helium and lithium. Okay. Again, at the same time, aromatic compounds involve a delocalization of pi electrons. These electrons obey Huckel's rule. Okay, for n, there's a rule, Huckel's rule, for n plus 2 rule, Huckel's rule. Okay, now it can be noted that some electron deficient molecules such as boranes and carboranes follow Wade's rules in order to attain stability. These molecules feature 3C2E bonds, 3 centered bonds in which 2 electrons are shared by 3 atoms. Okay. Now, the expanded octet hypervalency. Some main group elements have the ability to form hypervalent compounds. Expanded octet. Examples include sulfur hexafluoride SF6 and phosphorus pentachloride PCl5. If all the phosphorus chlorine bonds in PCl5 molecule are covalent, it would imply that the phosphorus molecule is violating the octet rule by holding a total number of 10 electrons. The formation of 5 bonds by the phosphorus molecules can be explained by the sp3 hybridization in PCl5 molecule. Okay, so remember here 1s orbital, 3p orbital and 1d orbital undergo hybridization to form an sp3 hybrid orbital. So here in phosphorus pentachloride, the hybridization is sp3 and d. This is the hybridization which is happening in phosphorus pentachloride. Okay, and the structure of the hypervalent PCl5 molecule, it is a trigonal bipyramidal. Okay, see this bond angle 120, one bond angle is 120, the other one is 90 degrees. Okay, and all these orbitals are sp3 hybridized orbitals. Okay, now what is chemical bonding, that I will not tell again and again. Let's go to the next slides. Lewis theory of chemical bonding also, here also same thing. Then Lewis symbols for lithium, oxygen and neon, which will be discussed now. Okay, Lewis lithium, it has 1 electron in the valence shell, oxygen has 6 electrons, neon has 1, 2, 3, 4, 5, 7, 8, 8 electrons. So these are you represent the Lewis symbols. Okay, then coming to more important thing over here, Phagons rule. Phagons rule. We classify certain compounds as ionic and other compounds as covalent. Now, if we were to ask among the alkali chlorides which is the most ionic, to answer this kind of question, we employ Phagons rule as a tool. So, a cation is there and an anion is there. So, what happens? From the anion part, the outermost electrons are attracted by the cation. Okay, so now we will discuss the Phagons rule in much more detail. Now, to understand the Phagons rule, let us first understand a few terms over here. First is polarizing power. It is the extent to which a cation can polarize an atom. Cation always polarizes an anion. Polarize means it makes a pole in the anion. All the negative electrons are pulled towards and the central nucleus is thrown on the other side. It is proportional to charge density. Charge density is the ratio of charge to volume. Okay, ratio of charge to volume, charge density. Polarizing power, charge density, more is the charge density, greater is the polarizing power. So remember this over here, polarizing power is directly proportional to charge density. So more the charge density of the cation, greater is its polarizing power. Now the next word over here is polarizability. It is the extent to which an ion can be polarized. It can also be called as the ease with which an ion can be polarized. Polarization is the distortion of a spherically symmetric electron cloud to an unsymmetrical cloud. Okay. Now, after understanding the words polarizing power and polarizability, we will discuss the postulates of Phagons rule. Okay, very, very important. This is important. Okay. You will get questions from this also, postulates of Phagons Rule. Now there are three factors basically under Phagons Rule. First one is size of the ion. Size of the ion. Smaller the size of the cation, the cation must be small. The larger the size of the anion, greater is the covalent character of the ionic bond. Though the bond is ionic, but the covalent character will be greater if the size of the cation is small and the size of the anion is large, which means polarizing is more. Then the charge of the cation. Greater the charge of cation, greater is the covalent character of the ionic bond. So again, if the charge is more, polarization will definitely be higher. Then electronic configuration. For cations with same charge and size, the one with n-1 d and ns0 electron is found in transition elements have greater covalent character than the cation with ns2 and p6 electronic configuration. That means the very fact that there is presence of d orbital electrons for the cations, okay, they will have more polarizing power than the ones having ns2 and p electrons in their valence shell. Okay, so electronic configuration is also one of the factors which can define or lay down the postulates of Phagons rules. Okay, now this type of electronic configuration ns2 and p6 is generally found in alkali or alkaline earth metals. Okay, now moving to the next part over here, we come to the VSEPR theory. Now, coming to the VSEPR theory, this theory is used to predict the shape of the molecules, from the electron pairs that surround the central atoms of the molecule. So, BSEPR theory, valence shell electron pair repulsion theory. It is an important theory. By using this theory, the concept of this theory, it is possible for us to, predict the shape of the molecules. Now, the shape of the molecules are generally, predicted by keeping in mind, the important thing over here, that is the electron pair that surrounds the central atom of the molecule. Now, it's the VSEPR theory is based on the assumption that the molecule will take a shape such that electronic repulsion in the valence shell of that atom is minimized. Now, what is VSEPR theory? Let us try to understand that. Now, the valence shell electron pair repulsion theory, abbreviated as VSEPR theory, is based on the premise assumption that there is a repulsion between the pair of valence electrons in all atoms, and the atoms will always tend to rearrange themselves in a manner in which this electron pair repulsion is minimalized. This arrangement of atoms determines the geometry of the resulting molecule. Now you must have learnt about the structure of water molecules in your junior classes. Okay. Now there are two lone pair of electrons on the central oxygen atom, and there are two bonding pairs. Now these two lone pair of electrons present on the two lobes of the atomic orbitals, they repel each other. That is why this angle is affected. Okay, that's why this angle is affected in water molecule. Okay, now looking at the next slide over here. Now, based on the VSEPR theory, okay, the different geometries that molecules can assume, okay, is given below. Suppose a number of electron dense areas, if it is 2, then it is a linear molecule. Number of no lone pairs, okay. Number of electron dense areas, okay, trigonal planar. Number of lone pairs, okay, it is one lone pair is there, so it is a bent molecule. Like we'll talk about, examples will be discussed later on. Then electron dense areas 4, number of electron dense areas is 4. Okay, so it will have a tetrahedral electron pair geometry, tetrahedral, one lone pair, and then it will be a bent. Okay, similarly, number of electron dense areas 5, trigonal bipyramidal, lone pair 1, 2 and 3. For 6 it is octahedral. So remember, whenever the number of electron dense areas is 2, the shape of the molecule is linear. 3 it becomes trigonal planar, 4 it becomes tetrahedral, 5 it becomes trigonal bipyramidal, and 6 it becomes octahedral. So this is what you must remember over here under this heading. Now looking at the postulates of the VSEPR theory, the postulates. The first point, in polyatomic molecules, molecules which are made up of 3 or more atoms, one of the constituent atoms is identified as the central atom to which all other atoms belonging to the molecule are linked. Okay, so remember, in polyatomic molecules, the molecules made up of 3 or more atoms. 3 or more atoms, one of the constituent atoms is identified as the central atom. Somebody has to be there in the center, surrounded by other atoms over here. Okay, A, B, C and D. Okay, then the total number of valence shell electron pair decide the shape of the molecule. Very, very important point over here. The electron pairs have a tendency to orient themselves in a way that minimizes the electron-electron repulsion between them and maximizes the distance between them. Okay, the valence shell can be thought of as a sphere wherein the electron pairs are localized on the surface in such a way that the distance between them is maximized. Should the central atom of the molecule be surrounded by bond pairs of electrons, then the asymmetrically shaped molecule can be expected. So, if the central atom is fully surrounded by bonding electron pairs, then the asymmetrically shaped molecules which are asymmetrical can be expected. Otherwise, should the central atom be surrounded by both lone pairs and bond pairs of the electrons, the molecule would tend to have a distorted shape, not a regular shape, but it will have a distorted shape. Moreover, the VSEPR theory can be applied to each resonance structure of the molecule. Okay, the strength of the repulsion is strongest in 2 lone pairs and weakest in 2 bond pairs. So, repulsion, lone pair repulsion, lone pair repulsion is greater than lone pair bond pair, which is greater than bond pair repulsion. Remember this order. Okay, now if electron pairs around the central atom are closer to each other, they will repel each other. This results in an increase in the energy of the system, that is the molecules. If the electron pairs lie far from each other, the repulsion between them will be less and eventually the energy of the molecule will be low. So this is also another important point. So these are the postulates, but you will not get questions from this VSEPR theory to write on the postulate, but you have to apply the postulates to get the structure and shape of the molecules. Okay. Then, of course, there are some limitations to the VSEPR theory. Some significant limitations of the VSEPR theory include: this theory fails to explain isoelectronic species. Now, isoelectronic species means species having the same number of electrons. Okay, the species may vary in shape despite having the same number of electrons. Moreover, the VSEPR theory does not shed any light on the compounds of transition metals. Very bad over here. The structure of several such compounds cannot be correctly described by this theory. This is because the VSEPR theory does not take into account the associated sizes of the substituent groups and the lone pairs that are inactive. Okay. The another limitation of VSEPR theory is that it predicts that halides of group 2 elements will have a linear structure, whereas their actual structure is always a bent one. So these are some limitations of the VSEPR theory, my dear students. Okay. Now, how to predict the shape of the molecules? Now, the following steps must be followed in order to decide the shape of molecule. Number 1. The least electronegative atom must be selected as the central atom, since this atom has the highest ability to share its electrons with the other atoms belonging to the molecule. So remember this. The central atom is the selected one, which is the least electronegative atom. Okay. Then the total number of electrons belonging to the outermost shell of the central atom must be counted. must be taken into consideration. The total number of electrons belonging to the other atoms and used in bonds with the central atom must be also taken into account. These two values must be added in order to obtain the valence shell electron pair number of the VSEP number or the VSEP. That means, so we have to take into account the total number of electrons in the central atom in the valence shell and the total number of electrons in the atom which are surrounding the central atom. So this number is called, which is called valence shell electron pair number. Depending on this, it is possible for us to get the or predict the shape of the molecule, which can be understood very clearly from the next table below. Now, what is VSEP number? Valence shell electron pair number. This describes the shape of the molecule as discussed below over here. If the VSEP number is 2, then we will have a linear molecule. If it is 3, then trigonal planar. If it is 4, then tetrahedral. If it is 5, then trigonal bipyramidal. If it is 6, then it is octahedral. If it is 7, it is pentagonal bipyramidal. Okay. So try to remember this VSEPR number and the corresponding shapes. Okay. Now each of these corresponding shapes can also be found in the illustration provided earlier. That time I discussed about that. However, the VSEPR theory cannot be used to obtain the exact bond angles between the atoms in a molecule. So that is one drawback we can say. We cannot use the VSEPR theory to get the exact bond angles in molecules. Then linear shape of molecules, some examples will be discussed over here. In this type of molecule, we find two places in the valence shell of the central atom. They should be arranged in such a manner that repulsion can be minimized, pointing in the opposite direction. Example is beryllium difluoride. Beryllium difluoride, you see, beryllium BeF2, BeF2. Okay, if you draw the shape, it becomes BeF over here, another F over here. So remember, hydrogen, helium, lithium, beryllium. Beryllium, hydrogen, helium, lithium, beryllium. Its atomic number is 4. Its number of electrons in the valence shell is 2. That is why it has no lone pairs. It has only bonding pairs. Okay. So in this type of molecule, we find 3 molecules attached to the 2 molecules attached to the central atom. Now they are arranged in such a manner that such repulsion between the electrons can be minimized towards the corners of an equilateral triangle. This becomes BeF3. Sorry, what you call BeF3. Okay, BeF2 is correct only, but this they are talking about BeF3 over here. Okay, now now let us have a look at the next slide. Tetrahedral shape of molecule. Tetrahedral shape. If I talk about tetrahedral shape, you know, it is like this. Molecule is central atom is here, so this is the tetrahedral shape. In 2-dimensional molecules, atoms lie in the same plane, and if we place these conditions on methane, we will get a square planar geometry in which the bond angle between hydrogen carbon hydrogen is 90 degrees. Now, if we consider all these conditions for a 3-dimensional space over here, we get a tetrahedral molecule with the bond angle in the case of methane is 109 degrees 28 minutes towards the corners of an equilateral triangle. So that is a wonderful important thing to remember. Okay. Now coming to trigonal bipyramidal shape of molecule. Let us take the example of phosphorus pentafluoride. Here repulsion can be minimized by even distribution of electrons towards the corner of a trigonal pyramid. So PF5, you know, F here, one F here, one F here, okay, one F here, and another F over here. So this is PF5. This will be 120 degrees, this will be 90 degrees. Okay, so in trigonal bipyramid, this 3 positions lie along the equator of the molecule. That means this one, and this one. We can say this 3. They lie in the equator, along the equator of the molecule. The 2 positions lie along the axis perpendicular to the equatorial plane. That means this is up, this is down. Okay, so that is how we get the shape of trigonal bipyramidal shape of phosphorus pentafluoride molecule. Then we can of course use the VSEPR theory to predict the shape of molecules. Now, the strength of the repulsion between a lone pair and a bond pair of electrons lies in between the repulsion between lone pair and between two bond pairs. Okay, so based on this, try to remember this order, repulsion order. Lone pair greater than lone pair, bond pair. It is greater than bond pair, bond pair. Okay. Now, here, point number one. To use the VSEPR theory to predict the shape of the molecules, total number of electron pairs around the central atom is equal to half number of valence electrons of central atom plus number of atoms linked to central atom by single bonds. For negative ions, remember, add the number of electrons equal to the units of negative charge on the ions to the valence electrons of the central atom. Okay, so this will be clear only if we do some examples later on in this chapter. Okay, now moving further, how to write the Lewis structures. How to write the Lewis structures? There are some steps given over here. Calculate the number of electrons required for drawing the structure by adding the valence electrons of the combining atoms. For example, in methane CH4 molecule, there are altogether 8 valence electrons, in which 4 belong to carbon while the 4 other belongs to 4 hydrogen atoms. Now, each negative charge, that is for anions, we add an electron to the valence electrons, and for each positive charge, that is for cations, we subtract 1 electron from the valence electrons. That is a rule. Then step 3, using the chemical symbols of the combining atoms and construction a skeletal structure of the compound, divide the total number of electrons as bonding shared pair between the atoms in proportion to the total bonds. Step 4, the central position in the molecule is occupied by the least electronegative atom. I have been telling over here. The central position, the central atom in the molecule whose Lewis structure is to be drawn is taken as the least electronegative atom. Okay, hydrogen and fluorine generally occupy the terminal positions. Remember that. Okay, after distributing the shared pair of electrons for single bond, the remaining electrons pairs are used for multiple bonds or they constitute lone pairs. The basic requirements is that each bonded atom gets an octet number of electrons. Okay. Now one example is given over here. Please try to understand this example. The Lewis formula for carbon monoxide. How to draw? So count the total number of valence electrons of carbon and oxygen separately in the valence shell. So carbon it is coming 4 plus oxygen it is coming 6. So it is coming total 10. There are total number of 10 electrons. The skeletal structure of carbon monoxide is written as CO. Drawing a single bond between CO first. Over here they have done like this. Total number of electrons is 10. So what you do is write carbon oxygen side by side. Okay. Then first total number of electrons is 10 electrons belong to carbon and oxygen altogether. So first 1 2 single bond. Okay, 2 electrons, 8 electrons left. Another 2 electrons like this, another 2 electrons over here. So 1 2 3 4 5 6 is done. Then 7 8 9 10. So that is how we draw the Lewis structure of carbon monoxide molecule. Okay. So total number of electrons in the bonding and the lone pairs should be getting 10 electrons altogether. Okay. The other example is structure of nitrite. Nitrite over here. Nitrite NO2 minus 1 formula is there. There is NO2 minus 1. So count the total number of valence electrons of 1 nitrogen atom, 2 oxygen atoms, and the additional 1 negative charge equal to 1 electron is added. So total number of valence electrons becomes how much? Nitrogen is 5 plus, okay, 2 oxygen is 12 and 1 negative charge, that is 1. That is coming to 18 electrons altogether. So we have to distribute the 18 electrons between oxygen, nitrogen, oxygen. Between oxygen, nitrogen is the, you can say, least electronegative. Okay, so that's why it is placed as the central atom. So now the it is placed over here in this diagram over here. This structure does not complete octet on nitrogen if the remaining 2 electrons constitute of lone pair on. Therefore, we have a double bond between 1 nitrogen and one of the 2 oxygen atoms. The Lewis structure is given over here. Okay, so we have to check whether they are following the octet on 1 2 3 4 5 6 7 8. Okay, over here 1 2 3 4 5 7 8. Over here 1 2 3 4 5 6 7 8. Now this is a better structure for the nitrite ion. Okay, so Now, now bond characteristics, another important term in this chapter. Bond length. The first bond characteristics is called length of the bond length. Now, during chemical bonding, when the atoms come closer to each other, the attraction takes place between them and the potential energy of the system keeps on decreasing till a particular distance at which the potential energy is minimum. If the atoms come more closer, repulsion starts and again the potential energy of the system begins to increase. Okay, at equilibrium distance, the atoms keep on vibrating about their mean position. The equilibrium distance between the centers of the nuclei of the two bonded atoms is called its bond length. So that is the definition of here. So always make it a point to mention in your definition the equilibrium distance between the centers of the two nuclei of the combining atoms containing the two bonded atoms. It is called the bond length. It is generally expressed in angstrom or picometer. Now it is determined experimentally by X-ray diffraction technique or electron diffraction method or by spectroscopic method. The bond length in chemical bonding is the sum of their ionic radii in an ionic compound. In covalent compound, it is the sum of the covalent radii. Okay. For a covalent molecule AB, the bond length is generally given by the formula D is equal to Ra plus Rb. Okay. Now, the first characteristics, bond characteristics. The factors affecting the bond length. This is also important thing to understand. The first factor affecting the bond length is size of the atoms. The bond length increases with increase in the size of the atom. So here, hydrogen iodide, the bond length is more. So among the hydrides of the halogens, the longest bond length you will find in Hi. Okay. The next one is the multiplicity of bond. Means either whether it is a single bond or a double bond or a triple bond. Okay. Higher the multiplicity of a bond, shorter is the bond. So the bond length decreases with an increase in the bond order. Then we have type of hybridization. S orbital is smaller in size. S orbital, an S orbital is smaller in size. Greater the S character, shorter is the bond length. So if the S character is more, more, then the bond length will be shorter. Okay. Now coming to the next bond characteristics, which is called bond enthalpy. Now when atoms come close together, the energy is released due to the chemical bonding between them. The amount of energy required to break 1 mole of bonds of a type so as to separate the molecules into individual gaseous atoms, it is called bond dissociation enthalpy or bond enthalpy. Now this bond enthalpy is generally expressed in kilojoules per mole. Now remember over here, greater is the bond dissociation enthalpy, greater is the bond strength. Okay. So here you can see this important sentence under bond enthalpy. Greater is the bond dissociation enthalpy, greater will be the bond strength. Now, for example, for diatomic molecules like hydrogen, chlorine, oxygen, nitrogen, HCl, HBr, HI, the bond enthalpies are equal to their dissociation enthalpy. In case of polyatomic molecules, bond enthalpies are usually the average values because the dissociation energy varies with each type of bond. In water molecule, first OH bond enthalpy is 502 kilojoules per mole. The second bond enthalpy becomes higher. It becomes lower. It is 427 kilojoules per mole. So you have to take the average. Therefore, average bond enthalpy becomes 502 plus 427 divided by 2. That comes to 464.5 kilojoules per mole. So for polyatomic molecules, the bond enthalpy is called average. It is taken as the average values of the first bond dissociation and the second bond dissociation energies. Okay. Now, the factors again over here, factors affecting bond enthalpy in chemical bonding. The first factor is size of the atom. Greater the size of the atom, greater is the bond length and less is the bond dissociation energy. So remember over here, size of the atom becoming greater, okay, the bond length will become bigger, longer, and less will be the bond dissociation enthalpy. That means less is the bond strength during chemical bonding. That is first factor. The multiplicity of bonds. Greater is the multiplicity of the bond, greater is the bond dissociation enthalpy. Okay. The next factor is number of lone pairs of electrons present. More the number of lone pair of electrons present on the bonded atoms, greater is the repulsion between the atoms, and thus less is the bond dissociation enthalpy of the chemical bond. So, if the number of lone pair is higher, the bond dissociation enthalpy will be lesser. Then the bond angle. A bond is formed by the overlap of atomic orbitals. The direction of the overlap gives the direction of the bond. The angle between the lines representing the direction of the bond, that is the orbitals containing the bonding electron, it is called the bond angle. Now have a look at this, examples over here. Factors affecting bond enthalpy in chemical bonding. Okay, it has been discussed nicely over here. In methane molecule, the bond angle is 109 degrees 28 minutes. In ammonia molecule, it is 107, because this nitrogen has got a lone pair of electrons. That is why there is repulsion. Here there is no repulsion at all. That is why the bond angle is 109 degrees 28 minutes. In the case of water molecules, the central oxygen atom, it has two lone pair of electrons. That is why the repulsion between this lone pair is much higher. That is why the bond angle is becoming lesser. If you look at boron trifluoride, the angle is 120 degrees. Okay, trigonal planar molecule. The next bond characteristic is called bond order. In Lewis representation, the number of bonds present between two atoms is called the bond order. Greater the bond order, greater is the stability of the bond during chemical bonding. That is, greater is the bond enthalpy. Greater the bond order, shorter is the bond length. Very important sentence over here. Greater the bond order, shorter will be the bond length. Okay. Then, now let's talk about some resonance in chemical bonding. There are molecules and ions for which drawing a single Lewis structure is not possible. For example, we can write two structures for ozone. Learn these structures properly. Structure A, structure B for ozone. Resonating means a delocalization of pi electrons. One is a pi bond, sigma bond. So this pi electron delocalized between this oxygen and this oxygen. So in the second structure, it is over here. Now, structures A and B are called resonating or canonical structures, and C is the resonance hybrid. This phenomenon is called resonance, a situation in which more than one canonical structure can be written for a given species. The chemical activity of an atom is determined by the number of electrons in its valence shell. When, with the help of the concept of chemical bonding, one can define the structure of a compound and is used in many industries for manufacturing products in which the true structure cannot be written at all. So, here remember, in A, the oxygen-oxygen bond on the left is a double bond and the oxygen-oxygen bond on the right is a single bond. Okay, here. In B, the situation is just the opposite. The experiment shows, however, that the two bonds are identical. Therefore, neither structure A nor B can be correct. On the bonding pairs, one of the bonding pairs in ozone is spread over the region of all three atoms rather than localized on a particular oxygen atom, oxygen-oxygen bond. This delocalized bonding is a type of chemical bonding in which bonding pair of electrons are spread over a number of atoms rather than localized between two. Okay, so here we have a knowledge, some idea about the resonating structures, which are also called canonical forms. Okay, and this is the resonance hybrid over here. Resonance hybrid. Okay, resonance hybrid is normally it's written like this. It is written like this. Dotted lines. Okay, lone pair over here, two lone pairs over here, another two lone pairs. This is the resonance hybrid for ozone molecule. Okay. Now I will request you to practice these structures as examples of resonance, which I have already discussed in the past over here. Carbonate ion, please learn this. CO3 minus 2. Okay, this is the hybrid over here. Hybrid over here. These are the canonical forms. Okay, resonating forms over here. This is for the carboxylate ion. RCOO minus, RCOO minus. So resonance is happening this way, Okay, this is the hybrid. Then the difference in the energies of the canonical forms and resonance hybrid is called the resonance stabilization energy, RSE. Now coming to London dispersion forces. Another form of chemical bonding is caused by London dispersion forces. These forces are weak in magnitude or nature. Okay. So here you can see there is uneven distribution of electrons in helium. Okay. Now what happens because of this uneven distribution? Dipole is formed, two poles, negative pole over here and positive pole. Okay. So because of this, you will bring another neighboring helium atom. Induction happens. So induced dipole is created on the neighboring atom. So such a force. These forces occur due to temporary charge imbalance arising in an atom. This imbalance in the charge of the atom can induce dipole on neighboring atom. For example, the temporary positive charge on one area of an atom can attack the neighboring negative charge as well at the same time. Okay. Now, there is one theory which is an obsolete nowadays, which is called valence bond theory, VBT. According to the VBT, electrons in a molecule occupy atomic orbitals rather than molecular orbitals. The atomic orbitals overlap on the bond formation, and the larger the overlap, the stronger will be the bond. Now, many approaches have been put forth to explain the nature of bonding in coordination compounds. One of them is the valence bond theory. The valence bond theory was developed in order to explain chemical bonding using the method of quantum mechanics. This theory primarily focuses on the formation of individual bonds from the atomic orbitals of the participating atoms during the formation of a molecule. Okay. Now, some postulates are given over here with regard to the valence bond theory. We can just go through these postulates. Covalent bonds are formed when two valence orbitals, half-filled, belonging to two different atoms overlap on each other. The electron density in the area between the two bonding atoms increases as a result of this overlapping, thereby increasing the stability of the resulting molecule. Okay. So remember, how are covalent bonds formed according to the valence bond theory? When two valence orbital means outermost orbitals containing half-filled electrons. Okay. These belonging to different atoms overlap on each other. The electron density in the area between the two bonding atoms increases as a result of this overlapping, thereby increasing the stability of the resulting molecule. That is the first postulate. Then, the presence of many unpaired electrons in the valence shell of an atom enables it to form multiple bonds with other atoms. So, multiple bond takes place when a number of unpaired electrons are available over there on the atoms. Okay. Now, the paired electrons present in the valence shell do not take part in the formation of chemical bonds as per the valence bond theory. Now, the third point is covalent chemical bonds are directional and are also parallel to the region corresponding to atomic orbitals that are overlapping. Sigma bonds and pi bonds differ in the pattern that the atomic orbitals overlap. That is, pi bonds are formed from sidewise overlap of the orbitals, whereas the overlapping along the axis containing the nuclei of the two atoms leads to the formation of sigma bonds. So, sigma bonds forms like this, overlapping head-on. This will form a sigma bond. If the overlapping happens like this, this will form a pi bond. Okay. Then, please note that sigma bonds involve the head-to-head overlap of atomic orbitals, whereas pi bonds involve parallel overlapping, as I've already told you. Okay. Then, my dear students, number of orbitals and types of hybridization. This number of orbitals and types of hydrogen, according to the VBT, the metal atom or ion under the influence of ligands can use its n-1d orbital, ns orbital, np orbital, or ns orbital, np, nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar, and so on. These hybrid orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bond formation. Okay. So based on the valence bond theory, there is a chart over here which can help you, predict or estimate, come to a conclusion about the type of hybridization and the distribution of hybrid orbitals in shape to give a geometry, definite kind of geometry in the compound. So if the coordination number 4 means there are 4 ligands around the central atom. So if the coordination number is 4, then the possible type of hybridization is sp3, one s orbital and 3 p orbitals intermixing with each other to give a tetrahedral geometry of the molecule. Similarly, for 4, coordination number 4, this is also possible, dsp2, okay, square planar. For 5, it is sp3d, trigonal bipyramidal. For 6, sp3d2, octahedral. For again 6, it is d2sp3, inner orbital complex. The shape of the molecule will be octahedral. Okay. Now, there are a number of applications of the valence bond theory. Okay. So, applications, the uses, the maximum overlap condition which is described by the valence bond theory can explain the formation of covalent bonds in several molecules. This is one of its most important applications. For example, the difference in the length and the strength of the chemical bonds in hydrogen and fluorine molecules can be explained by the difference in the overlapping orbitals in these molecules. Then the covalent bond in HF molecule is formed from the overlap of its 1s orbital of the hydrogen atom and a 2p orbital belonging to the fluorine atom, which is explained by the valence bond theory. There are limitations to this valence bond theory as well. The valence bond theory fails to explain the tetravalency exhibited by carbon, a very important point. This valence bond theory does not give us information about the energies of the 2 electrons. This theory assumes that electrons are localized in specific areas, which is wrong. This theory does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. Moreover, this theory has no distinction between weak and strong ligands. It does not classify which are the weak ligands, which are the strong ligands. Moreover, no explanation for the color exhibited by coordination compounds has been successfully explained by this theory. Okay, so that is why the other theories came into existence, which is called the molecular orbital theory. Now, my dear students, I will continue the molecular orbital theory in my next video, which I will do in detail, and I will teach you how to draw molecular orbital energy diagrams after explaining you this theory in my next video. For today, thank you so much. Have a nice day.